Good evening, Doctor. This is Kamandatha from Group SWML 26, and I'm presenting my about our project, which is babesiosis detection in animals. These are the contents of the presentation that will be included in my slides. First of all, I shall have an introduction, explain how my models learn. This is a CNN model. These are CNN models. Basically, they are concentrated on the images. So they learn the same way, though they work different ways. So I'll explain my models, which is my model architecture that I worked on. For example, ResNet 18, the FisherNet B0, Mobile V2, and then the FisherNet B4. Then I'll be explaining how each model works, how the optimize and the normalization are, the simulations or the visualization that I managed to get after running the evaluation file. Then also the learning rate, conclusions and limitations, and then the acknowledgement. So I will start with the introduction. In this project for babesiosis detection, I will basically have four classes. Uh, and these include the babesiosis, which consists of the positive images which are diagnosed with babesiosis, the plasmodium images, which are negative, but they have a similar they resemble babesiosis. They resemble babesiosis, which creates confusion to some veterinary doctors, especially when they are trying to distinguish whether that is plasmodium cell or babesiosis. Then you have the red blood cells, which are negative images. These ones consist of images which are healthy, which are free from babesiosis. Then you also have the leukocytes, which also consists of the healthy cells, which gives us a more confidential level to distinguish between the healthy and then the unhealthy cells. So I've implemented the models using four model structures and all of the algorithms, and these include the ResNet 18, EfficientNet B0, MobileNet V2, and then EfficientNet B4. So this is how my model learns. Initially, we have the input data. So the model uses microscopy images of blood cells as the input, and these images are labeled into four classes: babesiosis, leukocyte, plasmodium, and then the normal red blood cells. This allows the model to learn how to distinguish between the infected and then the healthy cells. So from there, we shall go to the data argumentation. The data argumentation helps us to improve the model generalization. For example, we have different data argumentation techniques, and these include random resized crop as the initial one, whereby we shall standardize our images at a size of 224 by 224 pixels specifically, because when a user uploads the images, we'll be targeting that particular sizing of the cell so that we do our evaluation. Then you have the flipping horizontal and vertical, which helps our model to learn the orientation invariant in the features. Then you have the rotation for angles greater than 30, and then also below, which stimulates real world variations in microscope positioning. Microscopes are positioned different ways, so no matter the angle, our model should be able to understand or analyze the image. Then you have the color jitter, which adjusts the brightness and the contrast to handle staining differences in the cells. Then you have the feature extractions. We use the deep learning models like ResNet 18, EfficientNet B0, and then MobileNet V2, EfficientNet B4 as our feature extractors. And these models automatically learn important patterns from the images. So this is basically how the models learn. You have different layers. In the early layers, the model detects the edges and then the textures. Those are the initial layers. Then when you go deep in the layers, the model will be learning the cell shapes and then also the structures. And then the final layers, the model will be able to identify the parasitic specific patterns which are crucial for classification of the image. Then you have the positioning. The prediction. The model outputs probabilities for each of the classes. These probabilities indicate how confident the model is for each class. The class with the highest probability is selected as the final prediction. For example, if a user uploads the image, our model will be able to analyze it and then to give a prediction for each of the classes that was stated. If the cell is, or if the image is infected with babesiosis will have a will have a higher percentage, for example 99% or 92% or 96%, and then the rest of the percentage will be taken by other classes, showing how the plasmodium cell is taking its portion, the red blood cells, and then also the leukocyte. Then you have the loss calculation. We use the cross entropy loss, which measures how far the predicted probabilities are from the true labels. Since the data sets may be imbalanced, we apply the class weights. This ensures that minor classes, for example, the infected cells, are not ignored during training. Then we shall go to our model optimization. We shall use the background propagation to compute the gradient of the loss. These gradients show us how the model weights should change so as to reduce the errors. So we also use the Adam W optimizer with a learning rate of 0.001, to which adapts the learning rate for each parameter based on the history. Additionally, we have the Masenko staining normalization, which is applied to reduce the variations in the staining across different images, so as to improve the model to improve the model consistently. Then you have our model improvement. The model is trained over multiple epochs. Meaning it sees different data sets multiple times. For example, each epoch runs through all the data sets every after the second year epoch also runs all the data sets. The more our model runs multiple epoch, very many epoches, it will be able to understand and analyze every kind and every point of the cells. After each approach, we monitor the validation accuracy to check the performance on the unseen data that is done. Of course, we have a validation set which consists of the images that were not used in the training. So these partial images will be used in the validation accuracy, whereby we shall be testing on that set. Then to see our model, how accurate the model is. The best performing model is saved, and then is saved so as to avoid overfitting and ensure optimal results. So I'll start with ResNet 18 as my model architecture, my first model architecture. ResNet 18 is composed of an 18-layer deep neural network. It was specifically designed to solve the vanishing gradient problem, which makes deep learning uh, the deep networks difficulty. The training of deep network difficulty. ResNet 18 achieves this by using the concept called the residual learning. That's the major concept in ResNet 18. Then we have our residual blocks, basically there are 4 stages, and each stage is composed of the residual blocks. In the first stage, we have 2 blocks consisting of 64 filters. At the early stage, we are just looking at the basic features like the edges and then the textures. And then you have the second phase, the second grade, sorry, stage, which increases to 128 filters. Here, the model will be learning more detailed shapes and then the patterns within the cell. And then the third stage, which uses 256 filters, our model will be detecting the more complex structures and then our image or the cells. And then in the final stage, which is stage 4, the model the number of filters will be increased to 512. And at this level, the model captures very high level and abstract features, and then it can be able to distinguish whether the image is healthy or unhealthy. When we have some key features, one of them is one of the basic key features that we use. However, the skip or the residual connections, and these connections allow input of the layer to be added directly to its output, and this improves the training speed, convergence, and then also accuracy. Then you have another important feature, which is the global average pooling. And this one reduces each feature to a single value, which helps us reduce the model complexity and also prevents overfitting. Then you have the output layer, the last one, which is the output layer. And the output layer consists of the features like the fully connected layer, which extracts data from the average pooling, from the average pooling, the global average pooling. Then we have the softmax layer, which is the last layer, which extracts the values obtained from the fully connected layer and then displays them. And then displays the scores as probabilities for each class, and maybe sometimes they can be converted to percentages. For example, you can have like 92% babesiosis, like that. That particular probability that is being displayed, it is done in the softmax layer or the fully connected layer. So we have our Lucid chart that explains how the model architecture flows. Initially, we have the image input. Remember, our images are being resized used to the pixels of 224 by 224. First of all, we shall first begin with inputting our image sized to 224 by 224. Then the image is made up of three channels, and the R, D, and B. At this stage, the model only sees the raw pixels with no features yet. Then when you go to our first layer, which is the conv block, which is composed of the 64 filters. These filters in the first layer detect the basic features such as the edges, the lines, and then also the simple textures. And this is where the model starts learning the visual partners. Then you have the conv block 2, which is composed of 128 filters. And the second block increases. Remember, the first one had 64, and then the second one increases with 128 filters, allowing the model to capture more detailed features. And then at this level, the network begins detecting shapes and simple structures. The feature then maps the feature maps become more informative compared to the first layer. Then from there we shall go to our fourth layer, which consists of 256 filters, which allows the network to learn more complex patterns. This layer captures high-level features such as part of the objects or specific biological features. The model is now focusing on the meaningful regions within the image. The attention is given to particular sections to understand the deep and the complex parts of the images, so as to get a clear and better understanding of how these cells are structured and the rest. Then in the final layer, we have the 512 filters. This is the final layer. This layer extracts the very complex and abstract features, such as the full object representations. And at this stage, the model has a deep understanding of the image content, and it can easily distinguish between a healthy and unhealthy cell or image. Some of the important features that we cannot forget within this is the skip connections. Each layer is composed of the skip connections, or we can call them the residue connections. And these connections allow the model to pass information directly across the layers. That's why each layer has. So these skip connections are the ones that allow the information to be passed from one layer to another. So this prevents the vanishing gradients and also improves the learning in the deep networks. Then you have the global average pooling as the next layer. After the extraction that has been made in the above layers, we apply the global average pooling, and this converts each feature map into a single value by averaging. It also reduces the number of parameters, which helps us to prevent overfitting within our model training. Then you have the fully connected layer. This is one actually the final layer because it produces the output which is got from the average pooling layer into the final connected layer. And this layer performs the classification task. Outputs the probabilities for each class, for example. Then I'll go to the next layer, which is I'll be explaining how the model learns or the model works. The model works. First of all, I have our initial step, which is the input. We'll start with the GIMSA standard blood smear images, which are being resized to 224 by 224 pixels in RGB format. We have the core architecture. ResNet 18 is a deep convection neural network with 18 layers. It uses the residual or skip connection, which allows the model to pass information from one layer to another. This helps us to prevent the vanishing gradient and also allow the network to learn more effectively. So we have our prediction process. Initially, first you put the image, then you go to the convolution layer. Inside here, we shall have the extraction feature steps by step. We shall start with the edges, then the shapes, and then finally move to a more complex partners like the parasite structures. Then we shall go to the pooling layer, and inside the pooling layer, we shall be reducing the partial size while keeping the important features. Then we shall go to our fully connected layer, which uses features for making prediction. Then finally to the softmax layer, which converts the outputs into probabilities that are being displayed to the user. Then our output, the model selects the class with the highest probability and provides a confidence score for explaining predicting Babesiosis the high percentage compared to the normal red blood cell. Then from there, we shall go to our next model, which is the efficient net B0. Its core idea for it uses the concept of the compound scaling, unlike ResNet 18, which uses the ResNet the skip connections. This means the model scales the depth, width, and then image resolution together instead of increasing only one. So it does them together, the depth, width, and then also the image resolution. And the advantages of this is better with fewer resources, despite having only about 5.3 million parameters. It provides some it achieves some high accuracy. Then shall we go to the stem layer. The stem layer, which is inside the building blocks. The stem layer is the first layer of the network. It uses a 3 by 3 convolution with 32 filters and then also 2 strides. This reduces the image size while extracting basic features like the edges and then the texture. So we have our body. The MB-conv blocks consist of 7 stages, and the main part of the network is the body, which consists of the MB-conv blocks arranged in 7 stages. MB-conv is like the mobile inverted bottleneck in full. These blocks require efficient network as efficiency and then also performance. So we shall talk about the MB-conv inside the body. So each MB-conv block uses the mobile inverted bottleneck structure. Instead of directly compressing features, it expands the channels, applies the deepwise conversion, and then it also compresses back to fewer channels. And this reduces computation while maintaining the important information, while keeping the important information. Then from there, shall we go to the size and excitation, the squeeze and excitation. Efficient B0 includes the squeeze and excitation blocks. These help the network focus on the most important features. In simple terms, the model learns which features matter more and then puts more emphasis on them. Then you have the scaling. Scaling, it is from the range of 32 to 112 filters. As we move deeper into the network, the number of filters increases from 32 to 112, and this allows the model to learn more complex and abstract features at the deeper layers. Then you have the switch activation, which is smoother instead of the RLU. The switch is smoother and helps improve the gradient flow during training. This leads to better performance, especially within the deeper networks. Then from there, shall we go to our global average pooling. After the extraction, process, this is the next step, the average pooling, and this converts the feature maps into a single feature vector, which releases the number of parameters and also preventing the overfitting. Then from there, we have our final fully layer, which outputs the probabilities. This is the efficient B0 CD chart. Initially, as usual, we have first our image, then you go to the stem convolution, where you shall start with our 30 filters to do the basic features like the edge analyzing, the texture. Then from there, we go to our third layer, which consists of the MB conv blocks. Of course, we have 32 layers. It also analyzes the extraction features using the lightweight operations. Then you go to the second, which has 108 filters. For each year, it focuses on learning more detailed patterns and then the shapes. We have the fifth layer, which consists of 256 filters. It also analyzes the more complex and deeper presentations within the cells. Then you have our next layer, which consists of 112 filters. Uh, these layers are refine features and also improve the feature quality using efficient computation. And then you have our final layer, which is composed of 1,280 filters. Uh, this acts as the high-level feature aggregator before classification. Here, the model can be able to distinguish between the healthy and then unhealthy cells. Then from there, we have our global average pooling, which which converts each feature map into a single value. It also lists the dimensionality and which helps in preventing overfitting within our training of the model. Then from there, we have our final control layer, which computes the values obtained from the average pooling and then converts them into our probabilities including our target classes. Then also have the softmax layer, which displays the the probabilities for each class. Then from there we shall go to how it works. So initially it was also taking the input images to use the core architecture uses the compound scaling, which focuses on balancing the depth, the width, and also the image resolution to improve performance. It uses the conv blocks, which are efficient and powerful for feature extraction. Then we shall go to how it works. Initially we have the convolution layers, which do the learning. When we have different layers, these convolution layers. So we start with the first layer to the last layer, but inside between those layers, we have between those layers we shall be learning different things. For example, extracting the features from the edges, for to more complex to for initially we shall have in the first layer we shall have the analyzing of the images based on the edges and visualization, simple things. And then we go to deeper analyzing the patterns, analyzing the cell structures until we reach the more complex parts of the parasite patterns. So this is all done within the convolution layers. Then from there we shall have our from the convolution layer we shall have our pooling, which helps us to reduce the size of the data and fully connected layer, and then this marks the prediction. Then we shall have our softmax, which converts the output into probabilities. Since we are done with efficient before B0 architecture, we shall proceed to efficient net before architecture. Uh, Efficient net be introduced also uses the compound scaling, which means instead of randomly increasing layers or filters, it basically focuses on the scaling of depth, the width, and then also the image resolution together in a balanced way. This leads to a better performance compared to traditional scaling methods. Remember, B4 uses 5.3 parameters, but the advantage of B4, that was B0, then the advantage of B4, for it uses almost like 19 million parameters, which gives us a higher accuracy for complex tasks like the images using the medical image analysis. So we have the key building blocks. The stem is the first layer that extracts the basic features like the edges, textures, and also the standard convolution. We have the body. The body is made up of the MB conv blocks, which are efficient convolution units originally from mobile VNet. Then you have the these blocks also include. Remember, these blocks also include the squeeze, the squeeze and extraction, which helps the network to focus on most important features, that is time-based channel attention. So as we go deeper, the number of filters increases from 48 to 448, allowing the model to learn more complex patterns compared to B0. B4 has more layers, meaning it has a deeper feature extraction of our images. Then you have the activation and the final stages. The model uses the switch activation, which improves the gradient flow and then overall performance compared to RIU. So from there we shall have our global average pooling, which reduces the feature maps into a single vector and making the model more efficient and reducing overfitting. Then finally, we have our fully connected layer with softmax, which produces the class predictions, which are got from the average pooling and then displays them partially for each class. So this is our LCD chart for FissionNet before. We have our image input as the initial step, the stem configuration, then you have the first block. Remember, for each in the first blocks, we have extraction of simple things, for example, like the edges and then the textures. But as we go further, we analyze more complex structures, for example, like the cell parasites, and then also the complex biological features. Then from there, we have the global average pooling, which reduces. Then you should also talk about how efficient before works. Initially, have our input. The model takes the GIMP sustained blood smears as our input. The images are being received to pixels of 224 by 224 with RGB channels. This ensures consistency before feeding into the network. We have our core idea whereby we use the compound scaling, which helps us to use the compound scaling in order to balance the depth, the audit, and the resolution of the images. Remember, the efficient net before is composed of which is built with MB config blocks. Is built with MB config blocks, which are optimized for efficiency. Then this is how we process our images. Initially, after uploading our image in the model, our configuration layers starts their particular work. For example, analyzing the image, expanding, and then also applying the deepwise configuration plus the compressions. Then we have our feature learnings. Inside our feature learnings, as the image moves deeper into the layer into the network, it learns patterns step by step. First step, analyze the edges, then the shapes, and then finally the complex structures such as the parasites forms in the blood cells. Then you have our global average pooling, which focuses on which focuses on converting the feature maps into a compact presentation, which helps us to lower the computation cost and also prevent overfitting. Then from there we shall have our fully connected layer. The extracted features are then passed through the fully connected layer. This layer performs the classification tasks, and it will display the scores that are obtained from the global average pooling for each class. Then you shall use the softmax layer to display these probabilities, uh, particularly for each class. For example, if the scores of the probabilities are like 92% by base year, the presentation will be given out for that the analyzer or the vet doctor understands what is particularly taking place. So next we shall talk about our mobile VNet architecture. It uses the DeepWire. It has the input and the conversion as the initial steps. The image passes through a standard deconvolution layer. This extracts the best features while reducing the image size. Then we have our key blocks or the core ideas. The core ideas that could be the main component is the inverted D. The main component in the mobile VNet architecture is the inverted USD block, which expands features in a one-by-one configuration. Then also applies the deepwise configuration, which are efficient for feature link, and then the project back to low dimensions. So why we need the inverted residues, instead of going wide narrow, it goes narrow wide and narrow, so it keeps on interchanging. It's not a consistent pattern now from wide to narrow, but rather it goes to narrow wide narrow, so that it captures the image in every dimension, and this improves the efficiency while preserving the important features. Then from there we have our deepwise separable convolution, which this one is split in two ways. The deepwise, which is more concerned for each channel or the per channel filtering. Then you have the pointwise, which combines the channels at once. This greatly reduces computation. Then from there we shall have our residual connections, which is used when input and output sizes match. It helps us in better gradient flow and then also the training stability. Then you have different stages. We have t is equal to 1, c is equal to t implies for expansion factor, and then c implies for the number of channels. So from there you have our final layers consist of the global average pooling, which reduces features, and the fully connected layer, which performs the class classification by displaying the probabilities. Then you have our how it works, input images. It uses core ID of deepwise separable convolutions, valid residual blocks. Initially, we shall first upload the image. The processing of the image as usual. First of all, upload the image, then the post conversion processes each channel separately. Then next is the pointwise conversion, which combines the features, the inverted residual blocks so that preserve useful information across layers. So as the data flows through, the model lines features from edge to shapes and then to parasite structures. So after the pooling, after that, now the pooling reduces the spatial dimensions, and then finally we have the fluid connected layer, which makes the prediction, and then outputs it in a softmax layer in a probability format of the scores for each class. Then you have our list the charts. So we have some of the output results for efficient BNet 4, which emerged as one of the best models when I was training. Initially, first of all, we have our we have our confusion matrix. The confusion matrix shows how the model performs for each class. The diagonal values represent the correct predictions, while the off diagonal values indicate the mismatch functions. Shall begin with leukocyte. The leukocyte model performs perfectly with 138 correct predictions and there is no error. Then you have the red blood cells. The model also performs well with 855 correct predictions, though a few are mismatched as Babesia and the Plasmodium, as we see in our diagram or in our chart. Then you have Babesia, which has a strong performance, but a few samples are confused with other classes. For example, we have 3 in a Plasmodia and then 9 in our red blood cells. Then you have our Plasmodium, which is also detected with only minor confusion in the red blood cells. As we see, we have only just 6 only are confused with the red blood cells. So overall prediction lies in the diagonal, indicating high model accuracy and the reliability. Then the second chart is about the precisions, the core, and then the F1 scores. These metrics give a deeper evaluation of the model, how it performs for each class. The precision makes measures how many predicted positives are actually correct, and then the recall measures how many actual positives are correctly identified. Then the F1 score balances the precision and then also the recall. So we have the leukocyte, which achieves nearly a perfect score across all the metrics, showing excellent performance. The red blood cells also have a high precision and a strong F1 score, indicating reliable classification. Then the plasmodium has a high recall, meaning most true cases are detected, although the precision is slightly lower. Then you have the Babesia, which has the lowest precision, suggesting some fake positives, but recall remains still high. Then the overall performance of our model demonstrates a strong and balanced performance across all the classes, with only just minor improvements that are needed for Babesia classification. This was the model auditing report and the performance. So the table represents the performance of efficient before across the four classes: Babesia, leukocyte, Plasmodium, and then the red blood cells. The evaluation uses precisions, the recall, and the F1 scores, which together provide a balanced assessment of classification performance. Starting with the overall results, the model achieves an accuracy of 94.2%, indicating a strong and predictive performance on the tested data. The weighted F1 score of 0.945 confirms that the model performs consistently well in especially considering the class imbalances. Looking at the class-wise performance, leukocyte achieves a nearly perfect result for precisions of 1.000 and then F score of 0.9993. This shows that our model is highly reliable in identifying leukocytes with minor errors. Then you have the read write cell, which has a strongly performing F1 score of 0.962, and this indicates that the FHNet before handles dominant classes effectively. Then you have the Plasmodia that has a solid F1 score of 0.940, demonstrating a good balance between precision and then recall. And then the Babesia, which also has a comparatively lower performance with precision of 0.67, recall of 0.89, and then the F score of 0.765. This suggests that the model successfully takes the Babesia diseases case highly recall, but also produces more false positives, reducing the precision. And this challenge may rise due to high class similarity between the Babesia and the other parasites, and the limited class imbalance while doing training. That's all that I can explain on that. And then you have the outputs. These are for ResNet 18, well explained as the previous one. We also have the model editing performance. Then you have the learning rates. The learning rates scheduler, the learning rate monitors the validation actually so doing our training. So if there is no improvement between the three consecutive epochs, the learning rate is reduced by half, and this helps the model to slow down the learning as it approaches the model. As it approaches the optimal solution. As a result, the model can fine-tune weights more precisely and then also avoid overshooting. So we have our regression techniques that we came up with to prevent overfitting, and several regularization methods are applied. For example, we have a dropout of 0.4, which randomly disables 40% of the neurons during training, focusing the model to learn more robust features. The data augmentation like the rotation, flipping, color jitter, which increases the dataset diversity and also improve generalization. We have the weight decay in ADAM-W, which keeps the weight small, leading to smoother and more stable learning. So we have the early stopping and best model saving. The model is saved only when the validation accuracy improves. That's what we were doing. So early stopping and then also best model saving. The model is saved only when the validation accuracy improves, ensuring that we keep the best version. So if there's no progress for the several epochs, our training stops early to avoid overfitting. This ensures that the final model is the best generalizing model, and not just for one performance over all the training data. Then we shall have our conclusions and limitations. We successfully built and evaluated four models from scratch. That is ResNet 18, EfficientNet B0, MobileNet V2, and then EfficientNet B4. We achieved a strong performance for most of them. ResNet had almost 96% after 27 epochs, Efficient 94, and then ResNet also 92 after some several epochs. Then the limitations, one of them we are training from scratch. We have limited data, a CPU only training, no real-time inference or model deployment tested yet, but we are working on it and to be done as soon as possible. And then lastly, I want to send my acknowledgement to our supervisor, Dr. Galiwangu Marvin, for his guidance and support courses, the Mendel, which provided me with the datasets that I used, and also my team members that have also put in my efforts that to complete get the best of this.